In 2005, two physicists looked at the oldest light in the universe and saw something they weren't supposed to see. The cosmic microwave background, the afterglow of the Big Bang, maps by satellites orbiting 1 million miles from Earth, showed a pattern. Not the expected random scatter of hot and cold spots, but an alignment. The two largest structures in the entire observable universe, separated by 9 billion light-years of expansion, pointed in the same direction. And that direction, impossibly, lined up with the plane of Earth's orbit around the Sun. They called it the axis of evil. The name was half joke, half warning. If the pattern is real, it violates the cosmological principle, the foundation of modern cosmology, that says the universe looks the same in every direction, no matter where you stand. The principle that says Earth is nowhere special, that the cosmos has no center, no edge, no preferred axis. The alignment suggested otherwise. It suggested the largest structure in the cosmos might be linked to our solar system in a way nothing in physics leads us to expect. 3 spacecraft, 30 years of data, and the alignment is still there. So here is the question. Is this a coincidence written into the statistics of observing one universe from one point in space? Or is it a message, encoded in the oldest light we can see, that the universe is not what we thought it was? The first person to see the cosmic microwave background wasn't looking for it. In 1964, 2 engineers at Bell Telephone Laboratories in New Jersey, Arno Penzias and Robert Wilson, were trying to eliminate noise from a radio antenna. The antenna, a 20-foot horn reflector built for satellite communication, picked up a persistent hiss no matter where they pointed it. They checked the electronics. They cleared out pigeon nests. They even accounted for what they politely called a white dielectric material the pigeons had left behind inside the horn. The hiss remained. It came from every direction in the sky, day and night, summer and winter, with the same intensity. 30 miles away, at Princeton University, a team of cosmologists led by Robert Dick had been building their own detector to search for exactly this signal. When Dick heard about the Bell Labs hiss, he told his team, "Well, boys, we've been scooped." What Penzias and Wilson had found was the relic radiation from the Big Bang itself, light that had been traveling for 13.8 billion years, cooled by the expansion of space to a temperature just under 3 degrees above absolute zero. They shared the Nobel Prize in Physics in 1978. That temperature is 2.725 Kelvin. In Celsius, it is minus 270.4 degrees. In Fahrenheit, minus 454.8. It is the coldest natural thing in the universe that is not absolute zero, and it fills every cubic centimeter of space. If you could see microwaves the way you see visible light, the entire sky would glow with a faint, uniform wash of radiation. You are inside it right now. It passes through your body at the speed of light, about 400 photons per cubic centimeter per second, left over from a time when the universe was so hot that atoms could not yet form. Here is the strange part. The temperature is not perfectly uniform. In 1992, NASA's Cosmic Background Explorer, COBE, detected tiny fluctuations in that glow. Hot spots and cold spots, varying by about 10 millionths of a degree. These ripples, imprinted 380,000 years after the Big Bang, are the seeds of everything that exists now. Galaxies, stars, planets, all of it grew from those microdegree wrinkles in spacetime. COBE's lead scientists, John Mather and George Smoot, received the Nobel Prize in Physics on December 8, 2006, in Stockholm. The Nobel citation read, for their discovery of the blackbody form and anisotropy of the cosmic microwave background radiation. The word anisotropy means the universe looks slightly different depending on which way you look. The cosmic microwave background is anisotropic at the level of 1 part in 100,000. That much was expected. The standard model of cosmology, called lambda-CDM for dark energy and cold dark matter, predicted exactly this kind of small-scale lumpiness. What no one predicted was what COBE saw when it looked at the largest scales. The cosmic microwave background can be broken down into spherical harmonics, a way of describing patterns on a sphere, the same way a Fourier transform describes patterns in time. Each harmonic is called a multipole, labelled by a number L. The dipole is L equals 1, the quadrupole is L equals 2, the octupole is L equals 3. Higher numbers correspond to finer details. The quadrupole represents the largest scale structure in the entire observable universe, features that span roughly 90 degrees across the sky. The octupole is the next size down, about 60 degrees. In a statistically isotropic universe, a universe with no preferred direction, the quadrupole and octupole should point in random, unrelated directions. The power in each multipole should be spread evenly across all possible orientations. COBE measured the quadrupole and found it weak, weaker than the lambda CDM model predicted by about a factor of 5. It measured 200 microkelvins squared of power, where the model expected around 1200. The probability of drawing a quadrupole that low from the standard model is somewhere between 0.7% and 4%, depending on how you count. Unusual, but not impossible. Cosmologists noted it and moved on. Then, in 2001, NASA launched the Wilkinson Microwave Anisotropy Probe. WMAP was named after David Wilkinson, a Princeton physicist who had worked with Dickey's team in the 1960s and helped design the probe before his death in 2002. It launched on June 30, 2001 from Cape Canaveral on a Delta II rocket. It traveled to the second Lagrange point, L2, a gravitationally stable location about 1 million miles from Earth in the direction opposite the Sun, where Earth's and Sun's gravity balance in a way that lets a spacecraft stay put with minimal fuel. WMAP carried 5 microwave detectors, observing at frequencies from 23 to 94 GHz. Its angular resolution was 33 times sharper than COBE's. Its sensitivity was 45 times better. It spent 9 years mapping the entire sky, scanning the same patches over and over, averaging out noise, hunting for the faint cosmic signal buried under foregrounds, radio emission from our own galaxy, dust, the glow of our solar system. In February 2003, the WMAP team released their first-year data. The low quadrupole was still there, and now they could see the octupole clearly. When they decomposed the octupole into its spherical harmonic components, they found something unexpected. Most of the octupole's power, 94% of it, sat in a single mode. That mode had a preferred axis. It pointed in a specific direction on the sky. 2 cosmologists, Angelica de Oliveira Costa at the Max Planck Institute and Max Tegmark at the University of Pennsylvania, noticed that the quadrupole axis and the octupole axis were nearly aligned. The angle between them was about 13 degrees. In a statistically isotropic universe, those 2 axes should be independent. The chance of them lining up that closely by accident was around 1%. Then, in 2005, Kate Land and João Magajo, at Imperial College London and the University of Oxford, published a paper in Physical Review Letters titled Examination of Evidence for a Preferred Axis in the Cosmic Radiation Anisotropy. They extended the analysis to higher multipoles. They found that not just the quadrupole and octupole, but also multipoles L equals 4 and L equals 5 shared a common preferred direction. They measured the average angle between the axes of these multipoles and compared it to 5,000 Monte Carlo simulations of statistically isotropic skies. Only 5 of those 5,000 simulations had a smaller average axis angle than the real sky. That is a 99.9% confidence level for rejecting statistical isotropy. In the paper's title and abstract, Land and Magajo used a phrase they had borrowed from then US President George W. Bush's description of North Korea, Iran, and Iraq. They called the alignment the axis of evil. The term stuck. Not because it was precise, it wasn't, but because it captured the discomfort cosmologists felt. The cosmological principle, the assumption that the universe has no special directions, is not just a convenience. It is the symmetry that makes Einstein's field equations solvable. Without it, general relativity becomes an intractable mess of 10 coupled nonlinear partial differential equations with no unique solution. The principle is the reason we can write down a single model, lambda CDM, that describes the entire cosmos with just 6 numbers. If the axis is real, that foundation cracks. João Magejo is a Portuguese physicist born in 1967, known for his work on varying speed of light theories as an alternative to inflation. Kate Land is a British astrophysicist who earned her doctorate at Imperial College and later worked at Oxford. In the 2005 paper, they wrote, "We are unable to blame these effects on foreground contamination or large-scale systematic errors." They checked. They tested whether galactic emission, synchrotron radiation from cosmic rays spiraling in magnetic fields, thermal radiation from interstellar dust, the glow of carbon monoxide, could be leaking into their maps. They applied masks to remove the regions near the galactic plane where foreground emission is strongest. The alignment remained. They tested different component separation methods, different ways of subtracting the foregrounds. Same result. They split the sky into hemispheres. The alignment was there in both halves. Here is what made it strange. The axis they found pointed roughly toward galactic coordinates longitude 260 degrees, latitude 60 degrees. That direction sits near the boundary of the constellations Virgo and Leo, close to, but not exactly at, the direction of the cosmic microwave background dipole. The dipole is the L equals 1 mode, and it is not a mystery. It is caused by our motion through space. The solar system, carried by the Milky Way, carried by the local group of galaxies, is moving at 369.82 kilometers per second, about 827,000 miles per hour, relative to the rest frame defined by the cosmic microwave background. That motion Doppler shifts the photons. In the direction we are moving, the radiation looks slightly hotter. In the opposite direction, slightly colder. The dipole amplitude is 3.3621 millikelvins, measured by the Planck satellite to a precision of 1 part in 3,000. The direction is galactic longitude 264.02 degrees, latitude 48.25 degrees, on the boundary between the constellations Crater and Leo. The axis of evil sits roughly 28 degrees away from that. Not perfectly aligned, but close enough to make people uncomfortable. And it sits close to something else, the ecliptic. The ecliptic is the plane of Earth's orbit around the Sun, projected onto the sky. From our perspective, the Sun traces a path through the constellations along the ecliptic over the course of a year. The ecliptic is defined entirely by local geometry. The tilt of Earth's spin axis relative to its orbital plane, the shape and orientation of that orbit in space. It has nothing to do with the large-scale structure of the universe. It is 9 billion years younger than the cosmic microwave background. The quadrupole octupole alignment axis lies within about 10 degrees of the ecliptic plane. The cosmic microwave background's 2 largest features, spanning scales of 9 billion light-years, appear to know about the plane on which a single rocky planet, in one unremarkable star system, orbits its star. Why does this matter? Because it suggests one of 3 things. 1. The alignment is a statistical fluke, a rare draw from an isotropic distribution that only looks suspicious because we picked it out after seeing the data. 2. There is a foreground, something local to our solar system, some glow or systematic error that we have failed to remove, That contaminates the measurement and makes the cosmic signal look aligned with our local geometry. 3. The alignment is real, and the cosmological principle is wrong. In 2007, Land and Magajo published a follow-up paper in Monthly Notices of the Royal Astronomical Society titled The Axis of Evil Revisited. They refined their statistics and tested different models of what a preferred axis might mean. They found the significance held at 94 to 98% confidence, depending on the exact method. They concluded, the alignment of the low multipoles is unlikely to be a chance event. But there is a problem with that conclusion, and it is called cosmic variance. Think about flipping a coin 5 times. You can get anywhere from 0 heads to 5 heads, and each outcome has a probability you can calculate. If you get 5 heads in a row, that is unusual. It happens only 3% of the time, but it is not impossible. If you flip the coin 1,000,000 times, patterns dissolve. The law of large numbers takes over. You will get very close to 50% heads. But if you only have 5 flips, you are stuck with high variance. One trial is not enough to say whether the coin is fair. The cosmic microwave background quadrupole has 5 independent pieces of information. For an isotropic Gaussian random field, the kind lambda CDM predicts, each component is an independent random draw from a distribution with a fixed variance. That variance is called C2, the quadrupole power. Because there are only 5 numbers, and because we observe only one universe, the uncertainty on the measured quadrupole power is large. The fractional uncertainty in CL equals the square root of 2 divided by 2L plus 1. For L equals 2, that is the square root of 2 over 5, or about 63%. Measuring the quadrupole from one sky is like flipping 5 coins once and trying to infer whether the coin is fair. You cannot be sure. The octupole has 7 modes. Its cosmic variance is 53%. These are irreducible limits. No amount of better instruments, no amount of longer observation can shrink them. We have exactly one observable universe. The low multipoles will always be uncertain, and any anomaly at those scales will always be hard to confirm. This is the argument Charles Bennett, the principal investigator of WMAP, made in a 2011 paper published in the Astrophysical Journal Supplement series. The paper, authored by Bennett and his team at Johns Hopkins University, was titled 7-Year Wilkinson Microwave Anisotropy Probe Observations. Are there cosmic microwave background anomalies? Bennett's answer was cautious. He wrote, I do think there is a bit of a psychological effect. People want to find unusual things. He pointed out that the cosmic microwave background contains roughly 3 million independent measurements. 3 million pixels, 3 million chances to find a pattern. If you look hard enough, you will find something that looks like a 2 sigma or 3 sigma outlier. That is the look elsewhere effect. The question is whether you are seeing a real signal or just the tail of the noise distribution. Bennett's team ran a Bayesian analysis of the quadrupole, which accounts for foreground uncertainty and cosmic variance simultaneously. They found that the cumulative probability of the lambda CDM model producing a quadrupole as low as or lower than the observed one was 0.824, 82%. In other words, the low quadrupole is not anomalously low once you properly account for the one sky limit. It is just an unlucky draw. But Bennett's analysis did not address the alignment. It only addressed the amplitude. And it used a specific statistical framework, Bayesian inference with certain priors, that other groups argued was too conservative. The alignment, in particular, kept appearing in independent tests, using different methods on different datasets. In 2009, a team led by Craig Cope, Dragan Huterer, ik-schwarz, and Glenn Starkman published a review in Advances in Astronomy titled Large Angle Anomalies in the CMB. Cope is a physicist at Case Western Reserve University. Huterer is at the University of Michigan. Schwarz is at Bielefeld University in Germany. Starkman, also at Case Western Reserve, is one of the most persistent skeptics of the standard cosmological model. In the review, they summarized a decade of low multipole studies and concluded, despite numerous detailed investigations, we still lack a clear understanding of these large-scale features, which seem to imply a violation of statistical isotropy and scale invariance of inflationary perturbations. They introduced a framework called multipole vectors, a way of representing each multipole as a set of unit vectors that encode the directions where the pattern peaks. For a perfectly isotropic field, those vectors should point in random directions. For the observed sky, the quadrupole vectors and octupole vectors clustered. The angle between the quadrupole plane and the octupole plane was about 6 degrees, depending on which component separation method you used. COBE's team calculated that the probability of such close alignment, given the cosmic variance uncertainty, was about 0.5%, roughly 3 standard deviations. 3 sigma is the threshold where physicists start to pay attention. It is not proof. Particle physicists do not claim a discovery until they reach 5 sigma, a 1 in 3.5 million chance of a false positive. But 3 sigma is the point where an anomaly becomes hard to ignore. And the anomaly was not just the alignment, it was also the low quadrupole, and also something called the missing large angle correlation. In a statistically isotropic universe, if you pick 2 points on the sky separated by more than about 60 degrees and measure their temperatures, those temperatures should be almost completely uncorrelated. The correlation function, the average product of the temperatures at 2 points as a function of their separation, should drop to near zero at large angles. The WMAP and Planck data showed something different. The large angle correlation was suppressed. Some measurements found it consistent with zero. Some found it slightly negative. COBE's team calculated the probability that lambda CDM would produce such a low correlation and found it less than 0.24% in cleaned maps. In one particular frequency channel, Planck's HFI 100 GHz map, the probability was as low as 0.03%. That is more than 3 sigma. It is a separate anomaly from the axis of evil, but it points in a similar direction. Something is wrong with the largest scales. Ik-schwarz gave an interview to New Scientist magazine in April 2016. The reporter, Michael Brooks, asked him whether the anomalies were fading as more data came in. Schwarz said, "For a long time, part of the community was hoping that this would go away, but it hasn't." In 2009, the European Space Agency launched Planck. Planck was named after Max Planck, the German physicist who founded quantum theory. It launched on May 14, 2009, from Kourou, French Guiana, on an Ariane 5 rocket, sharing the ride with the Herschel Space Observatory. It traveled to L2 and spent 4 years scanning the microwave sky with 9 frequency bands, from 30 to 857 GHz. Its angular resolution was about 5 to 7 arc minutes, roughly the size of a grain of sand seen from 10 meters away. Its temperature sensitivity was about 2 millionths of a degree, 2 parts per million of the mean cosmic microwave background temperature. Planck carried 2 instruments. The low-frequency instrument, LFI, observed at 30, 44, and 70 GHz using amplifiers cooled to 20 Kelvin. The high-frequency instrument, HFI, observed at 100, 143, 217, 353, 545, and 857 GHz using bolometers cooled to 0.1 Kelvin by a dilution refrigerator. 1/10 of a degree above absolute zero, colder than anything in nature. The first data release came in March 2013. In a paper called Planck 2013 Results 23, Isotropy and Statistics of the CMB. The Planck collaboration, a team of hundreds of scientists from across Europe and beyond, confirmed the anomalies. The quadrupole and octupole were aligned within about 9 to 13 degrees, depending on which component separation pipeline you used. Planck used 4 independent pipelines with names like SMECA, NILC, SEVM, and Commander. Each pipeline subtracts foregrounds differently. All 4 found the alignment. The probability to exceed, the chance that an isotropic universe would produce such close alignment, was listed as 1.2 to 3.4%, depending on the method. That corresponds to between 2.5 and 3 sigma. The Planck paper included a careful qualifier. A satisfactory explanation based on physically motivated models is still lacking. In 2015, Planck released its full mission data. The anomalies remained. In 2018, the team released the third data release, called PR3. In 2020, they released PR4, a reprocessing of the HFI data with improved calibration. Each time, the axis of evil was still there. But so was the caution. The Planck team, in their 2018 isotropy paper, wrote that the large angle anomalies are consistent with statistical fluctuations when cosmic variance is properly accounted for. They emphasized that the significance is modest, around 3 sigma, and that the look elsewhere effect is severe when you have millions of modes to examine. They also pointed out that the alignment is sensitive to how you mask the galaxy. If you cut out a large strip along the galactic plane, the significance drops. This is the foreground residual argument. The idea is that even after component separation, even after you think you have subtracted all the galactic synchrotron and dust and free emission, there might be a faint residual left over. And because the Milky Way is a disk-like structure, and because we observe the cosmic microwave background from inside that disk, any residual galactic contamination will have a preferred direction aligned with the galactic plane. The galactic plane is tilted about 60 degrees relative to the ecliptic, so a galactic residual could, in principle, produce an alignment that looks like it points toward the ecliptic. Anne Rosat and Jean-Luc Starck, cosmologists in France, published a paper in 2014 testing this idea. They used different masks and different component separation methods and found that the significance of several low multipole anomalies, including the axis of evil, depended on which mask you chose. When they used the most aggressive masks, cutting out the dirtiest regions, some of the anomalies disappeared. They concluded that foreground contamination could not be ruled out as the source. But there is a counter-argument. If the alignment is caused by galactic foregrounds, why do all 4 Planck pipelines, built by independent teams using independent methods, find the same axis? And why does WMAP, which flew a decade earlier with completely different detectors and a completely different orbit, see the same alignment? In 2022, the Beyond Planck project, a collaboration that reprocessed the Planck data using a fully Bayesian framework, published a paper revisiting the low quadrupole. They found that different versions of the WMAP and Planck data give quadrupole amplitudes that differ by more than 8 standard deviations. The WMAP 7-year and 9-year releases, which used identical masks, reported quadrupole values of 201 and 151 microkelvins squared, numbers that should agree if the measurement is robust. Planck's 2013 and 2018 releases reported 299 and 226. The differences are larger than the stated uncertainties. This does not mean the measurements are wrong. It means that the largest structure in the universe is hard to measure from inside it. Every pipeline makes different choices about how to model foregrounds, how to define the mask, how to propagate uncertainties. Those choices matter at low multipoles, where the signal is weak and the foreground-to-signal ratio is high. The quadrupole is the hardest number in cosmology to pin down, but the axis, the direction, is more robust. You can change the mask, change the pipeline, reprocess the data, and the quadrupole-octupole alignment persists. That is harder to explain away as a foreground artifact. Here is the other thing that is hard to explain: the ecliptic. The ecliptic is defined by 2 numbers. One is the obliquity, the tilt of Earth's rotation axis relative to the plane of its orbit, currently 23.4 degrees, and slowly decreasing due to gravitational torques from the Moon and Sun. The other is the direction of the vernal equinox, the point where the Sun crosses the celestial equator, moving north each March, currently drifting westward through the constellation Pisces due to the precession of Earth's axis. None of this has anything to do with the cosmic microwave background. The ecliptic is a coordinate system based on the motion of one planet in one star system. The cosmic microwave background is the relic radiation from the entire observable universe, emitted when the cosmos was 380,000 years old, and space was filled with a hot, dense plasma of electrons and protons, just beginning to cool enough for neutral hydrogen to form. That plasma filled a sphere now 46 billion light-years in radius, centered on us only because light has had 13.8 billion years to reach us. There is no causal connection between the ecliptic and the structure of the cosmic microwave background. The ecliptic did not exist when the cosmic microwave background was emitted. Earth did not exist. The Sun did not exist. The Milky Way was still assembling. Yet the quadrupole-octupole axis lies within 10 degrees of the ecliptic plane. And when you split the cosmic microwave background sky along that axis into a northern hemisphere and a southern hemisphere defined by the axis, you find that the northern hemisphere is slightly cooler than the southern hemisphere. This is called the hemispherical power asymmetry. It was first noticed in the WMAP data in 2007 and confirmed by Planck. The asymmetry is small, about 7% in power, and it is strongest at low multipoles. It is also aligned with the quadrupole-octupole axis, and therefore with the ecliptic. Why should the universe have a top and a bottom defined by the plane of Earth's orbit? The simplest answer is, it shouldn't, and it doesn't. It is a coincidence. The ecliptic is a convenient reference frame for observing from Earth, so we naturally notice patterns aligned with it. The cosmic microwave background has millions of modes, millions of patterns, and some of them will inevitably appear to line up with our local geometry. We are seeing a few cherries we picked from a very large bowl and mistaking them for a signal. This is the mainstream view, and it is supported by a powerful result. In 2016, a team led by Daniela Sada and Hiranya Piris at University College London published a paper in Physical Review Letters titled, "How Isotropic is the Universe?" They tested whether the expansion of the universe itself, not just the small-scale temperature fluctuations, but the overall geometry, could be anisotropic. They used Planck data and compared it to a family of anisotropic cosmological models called Bianchi universes, which allow for global rotation or shear. They found that the odds against anisotropic expansion were 121,000 to 1. In other words, the universe expands isotropically to extremely high precision. If there is a preferred axis, it is not written into the large-scale dynamics of spacetime itself. But that test does not rule out primordial anisotropy, a preferred direction imprinted at the moment of the Big Bang, or even earlier, that affects only the pattern of fluctuations, not the expansion rate. And it does not explain the ecliptic correlation. Consider what it would take for the correlation to be a foreground effect, something local to the solar system. The most plausible candidate is cold dust. The solar system is embedded in a cloud of dust and ice, left over from comet tails and asteroid collisions and the slow evaporation of the Oort cloud, the shell of icy bodies that orbits the Sun at distances up to a light year. This cloud of material, called the zodiacal dust, glows faintly in the infrared. It is brightest in the plane of the ecliptic because that is where most of the material is. If there is cold dust in the outer solar system, dust cold enough to emit microwaves at the wavelengths Planck and WMAP observe, and if that dust is concentrated near the ecliptic, it could contaminate the cosmic microwave background maps. The contamination would be faint, just a few microkelvins, but the quadrupole amplitude is also only a few microkelvins. A small local foreground could bias the measurement. Craig COBE and his co-authors raised this possibility in a 2006 paper. They called it the Solar System Foreground Hypothesis, but they did not claim it was proven. They simply pointed out that no one had definitively ruled it out. In 2012, a team led by Frode Hansen in Norway tested the idea by looking for a correlation between the cosmic microwave background and the brightness of planets. If there is a heliospheric foreground, its amplitude should vary as the planets move through different parts of the zodiacal cloud. Hansen found no significant correlation. The test was not conclusive, but it did not support the foreground hypothesis. The alternative is that the alignment is cosmic, a feature of the primordial fluctuations themselves. If that is true, then one of three things is happening. 1. The cosmological principle is wrong, and the universe has a genuinely preferred direction on the largest scales. 2. The universe has some unusual topology. It wraps around on itself in a way that suppresses large-scale power and imprints alignments. 3. We are seeing the signature of new physics in the early universe, something that happened before inflation or during inflation that broke the symmetry and left a directional imprint. Each of these ideas has been explored. None has been confirmed. In 2005, the same year Land and Magejo coined the term axis of evil, a researcher named Tess Jaffe, working at NASA's Goddard Space Flight Center, published a paper in the astrophysical journal Letters. The title was Evidence of Vorticity and Shear at Large Angular Scales in the WMAP Data, a Violation of Cosmological Isotropy. Jaffe had tested whether a class of anisotropic cosmologies called Bianchi type 7H could explain the WMAP anomalies. Bianchi universes are homogeneous but not isotropic. They have the same density and pressure everywhere, so they obey the cosmological principle's requirement of homogeneity, but they allow for global rotation or shear, an overall spin or stretch in spacetime. A Bianchi 7H universe rotates and shears simultaneously, producing a spiral pattern in the cosmic microwave background. The pattern has a preferred axis, the rotation axis, and a characteristic scale set by the ratio of vorticity to shear. Jaffe fit the WMAP data to a Bianchi 7H template and found a surprisingly strong correlation. The best fit rotation axis pointed toward galactic coordinates longitude 222 degrees, latitude -62 degrees, not far from the axis of evil. When she subtracted the Bianchi template from the WMAP map, several of the low multipole anomalies disappeared. The low quadrupole became consistent with lambda CDM. The quadrupole-octupole alignment weakened. Even the cold spot, a separate anomaly, a region in the southern sky that is colder than expected, became less unusual. Here is the catch. The best-fit Bianchi model required cosmological parameters, values for the matter density and the expansion rate, that were incompatible with the standard lambda CDM model. In a follow-up paper in 2006, Jaffe and her collaborators tested whether you could have a Bianchi universe and also keep the concordance cosmology, and they found you could not. The Bianchi signal went away when you imposed the constraint that the universe is flat and accelerating, as the supernova data and the high multipole cosmic microwave background data required. In 2007, a team led by Michael Bridges in Cambridge published a paper in Monthly Notices of the Royal Astronomical Society that re-examined the Bianchi hypothesis using a more flexible statistical framework. When they allowed the rotation axis to vary freely over the whole sky, they found only weak evidence for a Bianchi signal, and the evidence turned slightly negative, meaning the data preferred no vorticity over vorticity. The Bianchi hypothesis is not dead, but it is not widely accepted. It remains a niche explanation that fits some of the data, but not all of it. Another exotic explanation is topology. In 2003, the same year the WMAP first-year data came out, a team led by Jean-Pierre Luminet, an astrophysicist at the Paris Observatory, published a paper in Nature titled Dodecahedral Space Topology as an Explanation for Weak Wide-Angle Temperature Correlations in the Cosmic Microwave Background. Luminet's idea was that the universe might be finite and wrapped, like the surface of a dodecahedron, a 12-sided solid. If you travel far enough in one direction, you come back from the opposite direction, like in the old video game Asteroids. The model is called Poincare dodecahedral space. Light traveling across this space takes shortcuts through the wraparound, and if the size of the dodecahedron is tuned just right, about 15 billion light-years across, matching the distance to the surface of last scattering, then the largest cosmic microwave background modes get suppressed because they do not fit inside the box. Luminet predicted that if Poincare dodecahedral space is correct, you should see 6 pairs of matched circles in the cosmic microwave background, places where the pattern repeats because you are seeing the same region of space from 2 different directions through the wraparound. Circles should have an angular radius of about 35 degrees and should show correlated temperature patterns. Teams searched for the circles. They did not find them. By 2008, follow-up studies using WMAP data had ruled out the simplest versions of Poincare dodecahedral space. Planck data strengthened the case against it. The universe, as far as we can tell, is consistent with being infinite and flat, not finite and wrapped. The dodecahedral model is now considered unlikely, though not entirely excluded. Other topologies, like a 3 torus, a universe shaped like a rectangular box with opposite sides glued together, are still possible, but they also predict features that have not been seen. Topology explains the low quadrupole naturally. If the universe is finite, wavelengths larger than the box size cannot fit, so the largest multipoles lose power. But topology does not obviously explain the alignment with the ecliptic. You would need the size and orientation of the box to conspire in just the right way, and that reintroduces a fine-tuning problem as severe as the one you were trying to solve. A third cosmic explanation invokes superhorizon modes, fluctuations on scales larger than the observable universe. In standard inflation, the fluctuations are generated by quantum noise in the inflaton field, the scalar field that drives the exponential expansion. The noise is random and statistically isotropic. But if there is a long wavelength mode, a ripple that spans scales far larger than what we can see, then our observable patch sits inside one crest or one trough of that wave. That imprints a preferred direction. This is the idea behind dipolar modulation, a model used to explain the hemispherical power asymmetry. The model says the cosmic microwave background temperature field is multiplied by a factor that grows in one direction and shrinks in the other, where the strength of the effect is a small number around 0.07, and the direction is set by a unit vector pointing toward the preferred axis. The result is that one hemisphere has slightly more power than the other. Dipolar modulation fits the hemispherical asymmetry well, but it is a description, not an explanation. It tells you the mathematical form of the pattern, but it does not tell you where the long wavelength mode comes from or why it points where it points. Some models propose that it is left over from a pre-inflationary phase, a time before the exponential expansion when the universe was small and could have been anisotropic. Others propose that it is a quantum fluctuation that happened to be unusually large on our horizon scale. Both are possible, but neither is testable, because we cannot see outside our horizon. There is also the possibility that the alignment is caused by something closer to home. Not dust in the outer solar system, but large-scale structure along the line of sight. The integrated Sachs-Wolf effect, ISW, describes how cosmic microwave background photons gain or lose energy when they pass through gravitational potentials that are changing in time. In a universe dominated by dark energy, voids are expanding and their gravitational wells are becoming shallower. A photon falling into a void gains energy, and if the void expands before the photon climbs out, the photon keeps some of that energy. The result is a hotspot in the cosmic microwave background. A region with an overdensity, like a supercluster, creates a cold spot. In 2015, a team led by Istvan Sapudi at the University of Hawaii published a paper in Monthly Notices of the Royal Astronomical Society, announcing the discovery of a supervoid aligned with the cosmic microwave background cold spot. The cold spot is a roughly 10-degree diameter region in the southern sky, in the direction of the constellation Eridanus, where the temperature is about 70 microkelvins colder than the average. It was first noticed in the WMAP data in 2004 and confirmed by Planck. It is one of the low multipole anomalies, though technically not part of the axis of evil, because it is a localized feature rather than a global alignment. Sapudi's team used galaxies from the Sloan Digital Sky Survey and other catalogues to map the three-dimensional distribution of matter along the line of sight to the cold spot. They found a void, a region about 1.8 billion light-years across, roughly 500 megaparsecs, where the density of galaxies is about 30% lower than average. The void sits at a redshift of around 0.2, which means the light from the galaxies there has been traveling for about 2 billion years. It is one of the largest voids known. In December 2021, a team using data from the Dark Energy Survey, DES, confirmed the supervoid using a technique called gravitational lensing. They measured how light from distant galaxies is bent by the gravity of the foreground void, and they found a lensing signal at a significance of more than 5 sigma. The void is real. But here is the problem. When you calculate the expected ISW temperature shift from a void of that size, using the standard lambda-CDM model and numerical simulations, you get about 10 to 20 microkelvins, not the 70 microkelvins observed. The void explains only a fraction of the cold spot. The lensing data, in fact, showed something unusual. The lensing signal around some of the supervoids in the field was about 30% stronger than the predictions from the Millennium and multi-dark N-body simulations, the standard benchmarks for large-scale structure. Some voids produced ISW amplitudes as large as 5.2 plus or minus 1.6 times the expected value. The discrepancies are not yet understood. The supervoid does not explain the quadrupole-octupole alignment. The cold spot is in a different part of the sky, and the void is only a few billion light-years away, far too small a scale to affect the quadrupole. The ISW effect operates on scales of hundreds of megaparsecs, not gigaparsecs. To shift the quadrupole, you would need a structure comparable in size to the horizon, and no such structure is known. But there is another large-scale anomaly that does not rely on the cosmic microwave background at all, and it is harder to dismiss. In February 2021, Nathan Seacrest, an astronomer at the United States Naval Observatory in Washington, D.C., published a paper in the astrophysical journal Letters titled "A Test of the Cosmological Principle with Quasars." He analyzed the sky distribution of 1.36 million quasars from the CatWise 2020 catalog, an infrared survey built from data taken by NASA's Wide Field Infrared Survey Explorer, WISE. Quasars are the brightest objects in the universe, supermassive black holes in the centers of distant galaxies, drinking in gas and shining with the luminosity of 1 trillion suns. They are visible across cosmological distances, out to redshifts of 6 or 7, when the universe was less than 1 billion years old. Because they are so distant and so numerous, they are ideal traces of the large-scale structure of the universe. If the cosmological principle holds, quasars should be distributed isotropically. The number of quasars in one direction should match the number in the opposite direction, on average, once you account for the kinematic dipole, the fact that our motion through space makes one hemisphere appear slightly brighter due to Doppler boosting, and the other slightly dimmer. The expected kinematic dipole for quasars is about 0.5% in amplitude, corresponding to our 370 km per second motion through the cosmic microwave background rest frame. Seacrest measured the quasar dipole and found an amplitude of about 1.6%, more than twice the kinematic expectation. The direction of the dipole was galactic longitude 238.2 degrees, latitude 28.8 degrees, 27.8 degrees away from the cosmic microwave background dipole. The probability of drawing such a large dipole from an isotropic distribution, given the uncertainties, was 5 times 10 to the minus 7. That is 4.9 sigma. In particle physics, 5 sigma is the threshold for claiming a discovery. 4.9 sigma is close enough to be alarming. Seacrest and his co-authors, including Subir Sarkar, a theoretical physicist at Oxford known for his skepticism of the standard cosmological model, wrote, "The dipole is inconsistent with the standard kinematic interpretation." They suggested 2 possibilities. 1. The quasar distribution is genuinely anisotropic, and the cosmological principle is violated on the largest observable scales. 2. There is a systematic error. Quasars in one hemisphere are systematically brighter or fainter than in the other, either due to dust extinction, or the survey selection function, or some other effect that mimics a dipole. In 2022, Seacrest published a follow-up combining the Quasar catalogue with radio survey data from the Very Large Arrays NVSS catalogue. The joint analysis gave a dipole significance of 5.1 sigma. In 2023, a team led by Rodrigo von Martins and Jailson Alcanis in Brazil published a Bayesian re-analysis in Physics of the Dark Universe, and they found the dipole significant at 5.7 sigma when combining all available quasar and radio data. In 2025, another team led by Sophia Boehm, analyzing radio sources from 3 surveys, NVSS, RACS, and LOTSS, found that the radio dipole is 3.67 times the kinematic expectation, with an uncertainty of 0.49, corresponding to 5.4 sigma. The quasar dipole does not depend on the cosmic microwave background. It is a completely independent probe of the large-scale structure of the universe. If it is real, it is the strongest evidence we have that the cosmological principle might be wrong. Suvi Ghazari, an astrophysicist who studies quasars, said in an interview that the result would be a huge discovery if true, but we need to rule out systematics first. One systematic that concerns astronomers is the evolution of the quasar luminosity function, the way the brightness distribution of quasars changes with redshift. If quasars in one hemisphere are, on average, at slightly different redshifts than quasars in the other, and if the luminosity function evolves, then that could create a dipole even in an isotropic universe. A paper by Jacques Wagenveld and Julian Darling in 2022 argued that exactly this kind of evolution could explain much of the dipole. But a counter-analysis by Rodrigo von Martins in 2024 found that evolution alone could not account for the full amplitude. Another concern is galactic extinction. Dust in the Milky Way absorbs light, and the absorption is strongest in the plane of the galaxy. If the quasar catalogues do not perfectly correct for extinction, then quasars behind the galactic plane will appear fainter and some will drop out of the sample. That creates a dipole aligned with the galactic plane, not the ecliptic or the cosmic microwave background dipole. But the observed quasar dipole does not point toward the galactic plane. It points near the cosmic microwave background dipole. At the time of writing, the quasar dipole is unresolved. It is being actively studied. The Dark Energy Spectroscopic Instrument, DESI, is mapping millions of galaxies and quasars across the sky with precise redshifts, and those data will test whether the dipole is real or artifact. The Euclid Space Telescope, launched on July 1, 2023, is mapping the weak gravitational lensing signal from 2 billion galaxies, which will provide an independent measure of the matter distribution on large scales. The Vera C. Rubin Observatory in Chile, scheduled for first light in 2025, will begin a 10-year survey of the entire southern sky, detecting billions of objects and tracking how the universe changes over time. If the quasar dipole survives these tests, then the axis of evil is no longer the only large-scale anomaly. it becomes part of a pattern. The cosmic microwave background dipole, the cosmic microwave background low multipole alignment, the hemispherical power asymmetry, and the matter dipole would all point in roughly similar directions. That would be hard to explain as a coincidence. But there is another large-scale anomaly, older and stranger, that also points in a similar direction. It is called dark flow. In 2008, Alexander Kashlinsky, a cosmologist at NASA's Goddard Space Flight Center, published a paper in the astrophysical journal Letters titled "A Measurement of Large-Scale Peculiar Velocities of Clusters of Galaxies, Results and Cosmological Implications." Kashlinsky and his team had used a technique called the kinematic Sunyaev-Zeldovich effect to measure the motion of galaxy clusters relative to the cosmic microwave background. The KSZ effect is a small temperature shift caused when cosmic microwave background photons scatter off electrons in the hot gas inside galaxy clusters. If the cluster is moving toward you, the photons get blue-shifted, cluster appears slightly hotter. If it is moving away, slightly colder. By measuring the KSZ signal for hundreds of clusters and stacking the data, Kashlinsky's team could measure the average velocity of clusters in different parts of the sky. In an isotropic, homogeneous universe, those velocities should average to zero over large enough scales. Any motion on scales larger than a few hundred megaparsecs should be washed out by the cosmic expansion. But Kashlinsky found a residual flow. Clusters across a huge patch of sky, extending from the constellation Centaurus through Hydra and Vela, were moving with a bulk velocity of around 600 to 1,000 kilometers per second in a common direction. He called it dark flow because the cause, whatever was pulling the clusters, was beyond the edge of the observable universe and therefore invisible. In 2010, Kashlinsky extended the analysis to clusters as far as 2.5 billion light-years away. The flow was still there. The direction was roughly toward galactic longitude 287 degrees, latitude 8 degrees, close to, but not exactly aligned with, the cosmic microwave background dipole and the quasar dipole. The result was controversial. Several teams tried to reproduce it and failed. A paper by the Planck collaboration in 2013 placed an upper limit on any large-scale KSZ signal and found that if dark flow exists, it must be less than about 254 kilometers per second. That is consistent with zero, given the uncertainties. Other studies using different methods, measuring the motion of galaxies directly from their redshifts, or using different cluster catalogues, found no evidence for a bulk flow on gigaparsec scales. Kashlinsky defended the result. In an interview, he said, "We don't have enough information to see what it is, but somewhere very far away the world is very different than what we see locally." He suggested that the flow might be caused by structure outside the cosmic horizon, matter distributions left over from an earlier era, or even a neighboring universe in an eternal inflation multiverse, pulling on our observable patch through gravity. Most cosmologists are skeptical. The KSZ effect is small, only a few microkelvins, and it is buried under much larger signals. The thermal Sunyaev-Zeldovich effect, the primary cosmic microwave background, point sources, instrumental noise. Extracting it requires careful modeling and assumptions about cluster properties, and small errors in those assumptions can produce spurious signals. The fact that Planck did not see it is strong evidence that it is not real, or at least not as large as Kashlinsky claimed. But if it is real, it would point in the same general direction as the axis of evil. That coincidence is hard to ignore. In 2006, Lawrence Krauss, a theoretical physicist then at Case Western Reserve University, wrote an essay for the online magazine Edge.org about the cosmic microwave background anomalies. He wrote, "The new results are either telling us that all of science is wrong and we're the center of the universe, or maybe the data is simply incorrect, or there is something wrong with our theories on the larger scales." He was being provocative, but he was also identifying the core discomfort. If the axis of evil is real and cosmic, it violates the cosmological principle. And if the cosmological principle is wrong, then Earth does sit near a special location, not the center of the universe, but on or near an axis of symmetry, an axis that should not exist. This is not the same as pre-Copernican geocentrism. No one is claiming the universe revolves around Earth. The claim is subtler, that the universe has a direction, and that direction happens to align with our local reference frame. It would be like finding that the continental plates on Earth are all drifting in a pattern that points at your hometown. Possible, but unsettling. George F. Stathiou, a cosmologist at the University of Cambridge and one of the architects of the lambda CDM model, published a paper in 2003 titled, "Is the low CMB quadrupole a signature of spatial curvature?" He speculated that the low quadrupole might reflect something about the global geometry of space, that the universe could be slightly closed, curved back on itself like the surface of a sphere, and that curvature suppresses the largest modes. He wrote, "The low-order multipoles, especially the quadrupole, have lower amplitudes than expected from this cosmology, indicating a need for new physics." But when Planck measured the curvature parameter, they found it consistent with 0. The universe is flat, or very nearly so. F. Stathiou's curvature explanation did not survive. In 2009, F. Stathiou published another paper, this time with Yichao Ma and Anthony Hansen, arguing that the significance of the low multipole anomalies had been overstated. They tested different statistics and different ways of accounting for the look elsewhere effect, and they found that once you correct for all the tests that have been done over the years, the combined significance of the anomalies drops. They did not claim the anomalies are gone. They claimed they are less significant than they appear at first glance. This is the central tension in the field. The anomalies are real features of the observed sky. Both WMAP and Planck see them, and they are too coherent to be instrument noise. But the significance is modest, around 3 sigma, and that is exactly the level where statistical flukes become plausible. 3 sigma means a 1 in 370 chance. In a 3 million mode dataset, you expect to find hundreds of 3 sigma outliers by chance. The question is whether this particular outlier is special because we chose it beforehand, or only because we noticed it after the fact. The strongest argument that it is not a fluke is the ecliptic correlation. That was not predicted by anyone. It was discovered after the data were released, but it is not a feature you would expect to find even in a large dataset unless there is a real connection. The probability of the largest cosmic structure aligning with a 9 billion year younger local plane is not something you can easily quantify, because it depends on how you define alignment and how many different local planes you could have tested. But intuitively, it feels wrong. It feels like the kind of thing that should not happen. Here is what makes the debate difficult. The cosmic microwave background is observed from one location in space and one moment in time. We cannot change our vantage point. We cannot rerun the experiment. We cannot observe a second universe. Every measurement we make is conditioned on the fact that we are here, in this galaxy, in this solar system, in this epoch, looking out at the last scattering surface from this one angle. Any feature that happens to align with our local reference frame is automatically suspicious, because we cannot tell whether it is a cosmic signal or a selection effect. This is called the anthropic problem, and it is especially severe at low multipoles, where cosmic variance is large and the number of independent measurements is small. There is a way to test the alignment that does not rely on temperature data. The cosmic microwave background is polarized. As photons scatter off electrons at last scattering, they pick up a preferred direction of oscillation. The polarization is encoded in 2 fields, called E mode and B mode, which describe different patterns of alignment on the sky. E modes are generated by density perturbations, the same fluctuations that produce the temperature anisotropies. B modes are generated by gravitational waves and by lensing of the E modes by large-scale structure. If the axis of evil is cosmic, it should leave an imprint in the E mode polarization, because the quadrupole and octupole temperature patterns are sourced by the same primordial density field that generates polarization. The Planck satellite measured polarization, but the data quality at low multipoles is limited by residual systematics, contamination from galactic foregrounds, and imperfect calibration of the instrument's polarization angle. The 2018 Planck Polarization Data Release, PR3, included low multipole polarization maps, but the team cautioned that the results are still affected by unresolved systematic effects. A follow-up analysis in 2020, PR4, improved the calibration, but the low multipole polarization signal remains noisy. Several groups have tried to test the axis of evil in polarization, and the results are inconclusive. Some analyses find hints of alignment between the temperature and E-mode multipoles. Others find no significant signal. The problem is that polarization is intrinsically fainter than temperature by about an order of magnitude. Galactic foregrounds are relatively brighter in polarization. Subtracting them is harder. Until we have cleaner polarization data, the polarization test of the axis of evil remains ambiguous. The next generation of cosmic microwave background experiments will help. Ground-based telescopes like the Simons Observatory in Chile and the South Pole Observatory, and a proposed space mission called LightBird, are designed to measure polarization with much higher sensitivity than Planck. They will focus on the B modes, hunting for the signature of primordial gravitational waves from inflation. But they will also improve the E-mode measurements at all scales. If the axis of evil is real and cosmic, those experiments should see it in polarization. If it is a temperature-only artifact, they will not. There is one more piece of evidence worth considering. In 2023, a paper titled "Strong Evidence Against the Statistically Isotropic Universe" was posted on the archive by a large international collaboration. The paper analyzed the Planck 2018 temperature and polarization data using a suite of isotropy tests and found multiple anomalies at high significance. The conclusion was blunt: statistical isotropy is strongly disfavored. But the cosmology community did not immediately accept the conclusion. The paper used a particular choice of statistical tests, and other researchers argued that the combined significance was inflated by not properly accounting for correlations between the tests. When you run 10 different tests and some of them measure the same underlying feature, you cannot simply multiply the p-values. You have to account for the fact that the tests are not independent. The debate continues. In 2025, a white paper called the Cosmoverse White Paper was circulated, summarizing the status of large-scale anomalies and calling for more theoretical work and more data. The document argued that the anomalies, taken together, warrant serious attention, but that no single anomaly is strong enough on its own to overturn the cosmological principle. This is where the field stands now. The axis of evil is a 3 sigma feature that has persisted for more than 20 years. It is seen by independent instruments. It is robust to changes in analysis methods. It aligns with our solar system's local geometry in a way that is not explained by any known foreground or systematic error. But it is also consistent, at the 3 sigma level, with a rare statistical fluctuation in an isotropic universe. And the full-sky isotropy tests, like Sardes-Bianchi analysis, show that the universe expands isotropically to very high precision. The weight of evidence best supports the mainstream position. The axis of evil is a real feature of the observed sky, but its significance is modest, and it is plausibly a rare but allowed outcome of the lambda CDM model, amplified by cosmic variance and the look elsewhere effect. WMAP and Planck see the same alignment because they are mapping the same sky, not because the instruments are correlated. The alignment's coincidence with the ecliptic and dipole is the hardest fact for this explanation to accommodate, and it remains unresolved. The higher significance, independent challenge to the cosmological principle comes from the quasar dipole. At nearly 5 sigma, and confirmed across multiple surveys and multiple analysis methods, the quasar dipole is harder to dismiss as a fluke. If it survives systematic checks, it will be the first robust evidence that the universe violates statistical isotropy on the largest observable scales. And if that is true, then the axis of evil may be part of the same signal, a faint, early hint of something we are only now beginning to see clearly. But we are not there yet. The quasar dipole could still be explained by survey systematics, by unmodeled quasar evolution, by subtle selection effects that no one has yet identified. The next 5 years of data from DESI, Euclid, and Rubin will settle the question. If the dipole is real, those surveys will confirm it. If it is artifact, they will show why. So where does that leave the axis of evil? Picture it this way. You are standing in a dark field at night, and someone hands you a compass. The needle points north. You trust the compass because it has always worked before. Then you notice something strange. The stars above you, faint, distant, barely visible, seem to form a pattern. And that pattern, impossibly, is aligned with the direction your compass points. Not perfectly, but close. You check the compass, it still points north. You check the stars, they are still aligned. You walk to a different part of the field. The alignment persists. You cannot explain it. Maybe it is coincidence. Maybe you are seeing a pattern that is not really there, a trick of the eye, the brain's habit of finding order in randomness. Maybe the compass is broken in a way you have not detected. Or maybe, just maybe, there is something about this field, something about the ground beneath you and the sky above, that creates a connection you did not expect. A connection between the local and the cosmic, between here and everywhere. The axis of evil is that compass and those stars. The cosmic microwave background is the sky, the oldest light we can see, emitted from the edge of the observable universe 13.8 billion years ago. The ecliptic is the compass, a reference frame defined by the orbit of our planet, a structure 9 billion years younger, 9 orders of magnitude smaller. They should have nothing to do with each other, but the data from 2 spacecraft across 2 decades says they might. No accepted mechanism explains it. Statistical isotropy says it should not exist. Cosmic variance says maybe it does exist, but only as a 1 in 370 accident. Foreground contamination says maybe it is not cosmic at all, just a faint glow from the outer solar system that no one has confirmed or ruled out. The Bianchi models, the topological models, the super-horizon mode models, all of them fit some of the data, but none of them fit all of it, and none of them predict the ecliptic correlation. What we know for sure is this. The quadrupole and octupole are aligned. The alignment has been measured by COBE, WMAP, and Planck. It is a real feature of the microwave sky. Its direction lies within 10 degrees of the ecliptic plane, and within roughly 30 degrees of the cosmic microwave background dipole. The quadrupole amplitude is lower than the lambda CDM model predicts, though the probability of such a low value is only a few percent, and the measurement depends sensitively on how you mask the galaxy and how you model foregrounds. The hemispherical power asymmetry, the fact that one half of the sky, split along the quadrupole-octupole axis, has slightly more power than the other, is confirmed at about 3 sigma. The missing large angle correlation, the fact that widely separated points on the sky are less correlated than lambda CDM predicts, is also confirmed at about 3 sigma. None of these facts alone is enough to overturn the standard model. Together, they form a pattern that is hard to ignore, but also hard to prove. That is the nature of low multipole cosmology. We are limited by the one sky. We cannot go back in time and watch the cosmic microwave background form. We cannot move to a different galaxy and observe the universe from a different angle. We have exactly 5 independent measurements of the quadrupole, and those 5 numbers must carry the weight of testing a theory that claims to describe the entire cosmos. The honest edge of our knowledge is here. We do not know whether the axis of evil is a cosmic signal or a statistical accident. We do not know whether the ecliptic correlation is a clue or a coincidence. We do not know whether the quasar dipole is the first crack in the cosmological principle or a systematic error we have not yet identified. The universe, on the largest scales, is hard to measure from inside it. Cosmic variance is a flaw, not a bug, and we are standing on that flaw. Some questions may not have more data. We may be at a permanent limit. But here is what we can say. The cosmological principle, the assumption that the universe is isotropic and homogeneous, is not a law of nature. It is a hypothesis. It is a simplification that has worked extraordinarily well at scales from tens of megaparsecs up to a few gigaparsecs. It is tested every time we map the large-scale structure of galaxies, every time we measure the expansion rate, every time we analyze the cosmic microwave background. And so far, at scales we can probe reliably, it holds. The SADA analysis, testing whether the universe expands anisotropically, found odds of 121,000 to 1 against. That is strong evidence, but it is not infinite evidence. The principle is tested, not proven. On the very largest scales, the scales probed by the quadrupole and octupole, the scales where cosmic variance is 60%, the scales where we only have one sky to look at, the principle is harder to test. The axis of evil sits exactly at that boundary. It is either the first hint that the principle fails at the largest scales, or it is a reminder that even a perfect principle will produce outliers if you only get one draw. Science cannot yet say which. The data are not strong enough. The quasar dipole may change that in the next few years, but even if it does, even if the dipole is confirmed at 10 sigma and the cosmological principle falls, that does not automatically mean the axis of evil was cosmic all along. The two anomalies could be unrelated, or they could be two facets of the same underlying isotropy violation, separated by 13 billion years of expansion and 9 orders of magnitude in scale. We do not know. And that is the real answer for now. Not, we don't know yet, implying we will know soon, but we don't know. And we may never know with certainty, because the universe gave us one sky, and the largest structures are measured with the largest uncertainties. And the distinction between a 3 sigma cosmic signal and a 3 sigma statistical fluke is a distinction that may be permanently ambiguous. Here is the part I find hard to stop thinking about. The axis of evil was named in 2005. In the 20 years since, we have built better instruments, collected more data, refined our statistics, tested dozens of explanations, and the axis is still there. It has not dissolved into noise. It has not been explained away by a foreground correction or a systematic error or a revised understanding of cosmic variance. Every new analysis either confirms it or finds it weaker but not gone. Every new test leaves it at roughly 3 sigma, significant enough to be interesting, but not significant enough to be conclusive. That is a strange place to be. Most anomalies in science either grow into discoveries or fade into irrelevance. The acceleration of the universe, discovered in the supernova data in the late 1990s, started as a 3 sigma hint and grew to a robust, multi-probe confirmation that earned a Nobel Prize. The faster-than-light neutrinos, announced by the Opera collaboration in 2011 at 6 sigma, turned out to be a loose fiber optic cable. The axis of evil has done neither. It has sat at 3 sigma for 2 decades, neither growing nor fading, waiting. Maybe that is its nature. Maybe the low multipoles are a domain where 3 sigma features live forever, because cosmic variance prevents them from becoming 5 sigma conformations. And our attachment to the cosmological principle prevents us from accepting them as real until they do. Or maybe the next generation of data will settle it. Maybe DESI will show that the quasar dipole is artifact, and the axis of evil will be reclassified as a fluke, a cautionary tale about confirmation bias and the look elsewhere effect. Or maybe DESI will confirm the dipole at 10 sigma, and the axis of evil will be reclassified as the first faint signal of a cosmic anisotropy we were too cautious to accept. Either way, the question was worth asking. The cosmological principle is not self-evident. It is a testable claim about the universe, and the axis of evil tested it. The result was ambiguous, but ambiguity is still information. We now know that the largest scales of the cosmos are more mysterious than the intermediate scales. We know that the quadrupole and octupole align, and that the alignment is not obviously explained by lambda CDM, and that the significance is right at the threshold where human intuition starts to fail. We know that the universe may have one last surprise hidden in the oldest light, or it may not, and that distinguishing those two possibilities is harder than we thought. That is what the axis of evil has taught us. Not that the cosmological principle is wrong, not that it is right, but that the question is live, and the answer is not yet settled, and the universe, on the largest scales we can see, is harder to read than we hoped. If you want to understand things this way, calmly, honestly, without hype or dread, just following the data to the edge of what we know and stopping there, then stay with us. There is always another question waiting on the other side of the one we just answered. And if the axis of evil is the kind of puzzle that draws you in, there is a related one we have explored before. The question of what it means when the universe's expansion history does not quite agree with itself, when two different ways of measuring the same number give two different answers. That tension, like this one, sits at the boundary of confirmed and unresolved. You will find it on the end screen. The axis of evil remains: one sky, 5 modes, and a direction the universe was not supposed to have. Whether accident or signal, it is still there, still unexplained, still waiting. Stay curious.